A very good morning to all. Now in this lecture 3 we are continuing the special purpose machines unit 6 to continue or to complete the remaining topics of this unit 6, and in lecture 2 we have covered the construction, working, characteristics and applications of synchronous induction motor and permanent magnet synchronous motor. Now the contents and outcome of this lecture. So in this lecture we'll cover single phase synchronous motors. So there are two types, reluctance motor and hysteresis motor, and the second lecture that we'll cover is the AC series motor. So on completion of these two types of special purpose machines, we will be able to describe the construction, working principle and applications of synchronous motors, and also we will be able to differentiate the DC series and AC series motors. Now, probable questions that may be asked. So first we'll see for AC series motor. So why should a series motor never be started on no load? I think we have studied this in electrical machines while studying the DC machines, DC series motor. Second question is, what is the constructional difference between the DC and single phase AC series motors? Comment clearly on the performance of a DC series motor when it is connected across the single phase AC supply. Means what? When a DC series motor is there with you and when it is connected to a single phase AC supply, then how it will perform. So we have to comment on that. Then describe the construction, working and applications of reluctance and hysteresis motors. Show that the synchronous hysteresis motor develops a running torque both at synchronous and asynchronous speed of the rotor. So these are few questions that may be asked on these two types of special purpose machines. So first we'll see the single phase synchronous motor, and one type of that single phase synchronous motor is reluctance motor. So first we'll see the construction, then operation, and then characteristics and applications. So construction. So as seen in the figure, so this is the rotor of reluctance motor. So the single phase synchronous motor, that is reluctance motor, it is similar to a split phase single phase induction motor. Now split phase single phase induction motor, we know that it is a type of one type of single phase induction motor. So it is similar to split phase single phase induction motor consisting of stator with main and auxiliary winding, starting switch in series with auxiliary winding, and salient squirrel cage rotor with poles. So this reluctance motor is similar to a split phase single phase induction motor, and constructionally it consists of stator, then starting switch and salient squirrel cage rotor with poles. Now the stator is with two types of windings, main winding and auxiliary winding. So the auxiliary winding is also known as starting winding in single phase induction motor. Why? Because it is used for starting purpose only, to start the induction motor. Because in single phase induction motor it is not possible to get the continuous torque. So to get the continuous torque we need one more winding, right? So to have a revolving flux. So to have a revolving flux, starting winding is used for starting period only. The salient squirrel cage rotor of reluctance motor is constructed by removing some of the teeth from the standard squirrel cage rotor, and the remaining teeth forms the salient poles as shown in figure, right? So here from this figure it is clear that in a reluctance motor whatever the rotor is there, and that is a salient squirrel cage type, and it is constructed by removing some of the teeth from the standard squirrel cage rotor. Means what? Whatever the squirrel cage rotor is there for conventional type of motor, then from that, by removing some of the teeth a rotor of reluctance motor is formed, right? And the number of poles created on the rotor must be equal to the number of stator poles. So here also the condition is that number of poles must be equal to the number of stator poles. So here how the poles are formed? By removing some of the teeth from the squirrel cage rotor, and remaining teeth form the salient poles. Got this? Now working principle or operation. The operating principle used in reluctance motor is: a force is exerted upon the ferromagnetic material, tending to bring it into the position of the densest portion of the field. Whenever the piece of the material is placed in a magnetic field, the force tends to align the piece of the material to a low reluctance path. For this, so how the movement occurs in this motor, that depends on the low reluctance path, right? So whatever the force is exerted upon the ferromagnetic material, that tends to bring it into the position of the densest portion of the field, right? So whenever the piece of the material is placed in a magnetic field, so then the force tends to align that piece of the material to a low reluctance path. When single phase AC supply is given to the motor starts as an induction motor, then accelerates and reaches to speed very close to synchronous speed. The slip is negligible when the mechanical load is small and the revolving field permanently magnetizes the salient pole or salient rotor poles, right? So whenever the single phase AC supply is to be given, then the we have to know that then the motor will start as an induction motor, right? Then accelerates and will reach to the approximate value of the synchronous speed, or will reach to the nearest value of the synchronous speed. Then the slip is negligible when the mechanical load is small and the revolving field permanently magnetizes the salient rotor poles. So the rotor poles then interlock with the opposite polarity stator field poles and runs at synchronous speed continuously. So here also the interlocking concept is used. That's why it is known as synchronous motor. Because here what will happen? The rotor poles interlock with the opposite polarity stator field poles, and that's why the motor runs at the synchronous speed continuously. The torque angle is adjusted by the motor with the change in load in the same way as that of three-phase synchronous motor. So with the increase in load, the motor may pull out of synchronism, and with the large load, the motor may not pull into synchronism, right? So I have to understand that the torque angle is adjusted by the motor with the change in load in the same way as that of the three-phase synchronous motor. So we have already studied this concept, torque angle in case of synchronous motor. So when the load on the motor is put, right, then the angle in between the uh, previous position of the rotor position of the motor is changed, right? And the angle in between that previous position and then the position when the load is put, that is known as torque angle, right? So the torque angle is adjusted with the load. So with the increase in load, the motor may pull out of synchronism, and with the large load, the motor may not pull into synchronism. So that must be keep in mind that it is dependent on the load. If the load on the motor is very large, then it is not possible to pull the motor into synchronism. And if we increase the load continuously, then motor may pull out of synchronism. Now characteristics and applications. The pull in and pull out torque of reluctance motor is small, and the motor is subjected to the cogging as the rotor torque varies with the rotor position. So the cogging effect can be reduced by skewing the rotor bars and by not having the number of rotor slots equal to an exact multiple of the number of poles. So how the cogging effect is reduced here? It is reduced by skewing the rotor bars. but not by having the number of rotor slots equal to the number of poles, exactly multiple of the number of poles. So these motors have poor power factor, low efficiency and poor torque. So these motors have poor power factor, low efficiency and poor torque. The reluctance motor is commonly used for constant speed applications like timing devices, signaling devices and recording instruments. So the applications are what? These types of machines are used in timing devices, signaling devices and recording instruments. Now the second single phase synchronous motor is the hysteresis motor. So first we will see the introduction. The small motors with constant speed characteristics are required for timing devices, so which operate from single phase AC supply. So these motors are known as single phase synchronous motors. So there is no need of DC source of supply for excitation. So these motors are used for driving electric clocks, record player, turntables, timing devices. But here, what is the limitation that we have seen in reluctance motor? That efficiency, output and developed torque is low. So what is the hysteresis motor? Constructionally, it is similar to a split phase induction motor, but no windings on rotor. It is similar to split phase induction motor, but no windings on rotor. It is non-salient pole type of construction. It consists of a stator with a permanent capacitor to develop a synchronously revolving field from single phase AC supply. It consists of rotor of magnetic material with high retentivity and permeability to have hysteresis effect. The magnetic material for the rotor should have large hysteresis loop, and special magnetic materials are used such as cobalt or chrome steel. The rotor may be smooth, solid, cylindrical in shape and does not carry any bar. Right? So it is as shown in figure. So here there is a shading coil, magnetic steel and exciting coil. So the constructionally it is similar to a single phase type of induction motor, and that type is split phase. And there is no any winding on the rotor. So it is a non-salient type of construction. So construction, it has a stator with a permanent capacitor, and what is the purpose of permanent capacitor here? To develop a synchronously revolving field from the single phase AC supply. Means for starting it is used to develop a starting torque. Right? Then it consists of rotor magnetic material, right, with high retentivity and permeability to have hysteresis effect. Right? So this is the hysteresis motor. But what is the drawback of this hysteresis motor? That efficiency, output and developed torque is low. And the rotor may be smooth solid cylindrical in shape, right? And does not carry any bar. Now continue to the single phase synchronous motor, and that is the hysteresis motor. Now we'll see the working principle of hysteresis motor. The operation of the hysteresis motor depends upon the hysteresis effect, due to which the magnetic field or magnetization lags behind the magnetizing force. So what is the working principle used here? It is the hysteresis effect, and that hysteresis effect will cause the magnetic field or magnetization lagging behind the magnetizing force. So when the single phase AC supply is given to the motor, a revolving field is developed which rotates at synchronous speed. The revolving stator flux magnetizes the rotor, but due to the effect of hysteresis, the axis of magnetization of rotor lags behind the axis of stator field by hysteresis lag angle, that is theta, as shown in figure A. So from figure A, it is clear that the axis of magnetization of rotor, that is indicated by axis of rotor magnetization, is lagging behind the axis of stator field by an angle theta. So the theta in between the stator field flux and axis of rotor magnetization indicates that the axis of rotor magnetization is lagging behind the axis of stator field. The instantaneous magnetic conditions in the air gap and rotor are as the shown in figure A. So what this indicates, these are the instantaneous magnetic conditions in the air gap, right, and in the rotor. The angle theta is hysteresis dependent and remains constant at all rotor speeds. The hysteresis torque due to the interaction between stator and rotor field is proportional to the product of stator flux, rotor flux, and since and sine of hysteresis angle theta means what? That the hysteresis torque due to the interaction between the stator and rotor field is proportional to the product of phi s, phi r, and the sine of the hysteresis angle theta means the hysteresis torque Th is directly proportional to the product of phi s, phi r, and sine of theta. Phi s is the stator flux, phi r is the rotor flux, and theta is the angle in between the rotor magnetization axis and stator field axis. Hence, hysteresis torque is constant at all speeds of rotor as shown in figure B. Right, so from figure B it is clear that the torque in Newton meter is constant throughout. For whatever the value of the synchronous speed in percentage, the torque in Newton meter is constant, having the same value. So due to eddy current loss, one more torque is developed in the motor at starting. So the motor starts under the influence of hysteresis and eddy current torque and finally attains the synchronous speed. So at synchronous speed there is no relative motion between stator field and the rotor, and as such there is no eddy current and no torque is developed due to it. So at synchronous speed the motor operates only due to hysteresis torque. At this speed the rotor develops magnetic poles similar to DC excited synchronous motor or the reluctance motor and adjusts its torque angle so as to develop the torque required by the load. Right, that's why it is known as hysteresis motor. Why? Because in hysteresis motor the torques due to two effects are formed. First is the due to the hysteresis effect, and then second effect is the eddy current loss. So the torque due to the hysteresis effect is given by the product of phi s, phi r, and sine of theta. But the torque due to the eddy current loss is negligible. Why? Because the motor starts under the influence of hysteresis and eddy current torque, right? But finally attains the synchronous speed. So at synchronous speed, as there is no relative motion between the stator field and the rotor, so there is no current, that is what, there is no eddy current, and that's why no any torque developed due to the eddy current. That's why the hysteresis motor will operate only due to the hysteresis effect, and that's why it is known as hysteresis motor. So at synchronous speed the motor operates only due to hysteresis torque, and whatever the speed is there, so that speed, so at this speed the rotor develops magnetic poles similar to the DC excited synchronous motor or the reluctance motor and adjusts the torque angle so as to develop the torque required by the load. So it is clear from the figure A and B, the working principle and the torque speed characteristics of hysteresis motor. Now we'll see the characteristics and applications of hysteresis motor. A hysteresis motor can accelerate the load whatever the inertia due to the development of uniform torque from standstill to synchronous speed. So just we have seen the torque and synchronous speed characteristics of hysteresis motor, and from that it is clear that the torque is constant throughout the speed, right? And that is why due to the development of the uniform torque from standstill to the synchronous speed. So the rotor with no windings or teeth made the motor operation quiet. There is no mechanical and magnetic vibrations, and that's why the noiseless operation due to resilient mountings, right? So that's why the ability of noiseless operation and to drive high inertia loads, the hysteresis motors are suited to drive timing devices, electric clocks and other precision audio equipment. So what are the applications of the hysteresis motor depending on the torque speed characteristics is that it has the ability of noiseless operation, and that's why it is able to drive high inertia loads, and that's why the hysteresis motors are generally used to drive timing devices, electric clocks and other precision audio equipment. Now AC series motor introduction. Direct current shunt or series motors rotate in the same direction regardless polarity of the supply. If the line terminals are reversed, both the field current and the armature current are reversed, and the torque developed remains in the same direction, and therefore the motor continues to rotate in the direction in which it was rotating before the line terminals were reversed, right? It is why it is due to the relation between the torque, current and flux. As we know that in DC machines, developed torque is directly proportional to the product of flux and armature current. So if we want to reverse the direction of rotation of the motor, then we have to reverse either the direction of the flux, means direction of the field current, or we have to reverse either the direction of the armature current. But if the supply is reversed, polarity of the supply is reversed, then both field current and the armature current will reverse and the motor will rotate in the same direction, right? So from this it seems that any DC motor would operate satisfactorily when connected to single phase AC supply, right? But it is not true. Why? Because it has been found that the shunt motor develops but little torque, quite little torque when it is connected to an AC supply. Means whatever the general decision motor is there, right, and when it is connected to the AC supply, then it develops little torque. So the field winding of shunt motor is wound with many turns of fine wire so as to limit the field current but to give high flux. So these many turns of wire cause a significant inductive effect resulting in a high reactance and so a high impedance. So the result is a very low field current, much lower than that required to develop sufficient starting torque. So there is another adverse effect of high inductance of the shunt field, right? So there is another adverse effect of high inductance of the shunt field. The high inductance of the shunt field causes the field current, and therefore the flux to lag nearly 90° in time with respect to the line voltage. So the rotor or armature current also lags behind the applied voltage, but because of its fewer turns, the angle lag cannot be large. So the time phase difference between the flux and the rotor current therefore is considerable, and since torque developed in an AC motor is proportional to flux, rotor current and the cosine of the angle between the two, the torque developed is further reduced. So for these reasons, the reduction of field current and time phase difference between the flux and the rotor current, a shunt motor will not develop sufficient starting or running torque when connected to single phase AC supply. That's why when we connect the normal DC motor to a single phase AC supply, then it is not possible to get the enough starting torque or running torque. So however, in case of series motor, the field is wound with relatively few turns of heavy wire, and therefore the inductive effect is less, and the field current and the flux are almost in phase with each other. The rotor current is of course the same in both field and rotor, and there is no time lag between the flux produced by the field coils and the current in the rotor conductors. Thus the two objections to the operation of a shunt motor on AC supply are overcome in the case of series motor, and it may operate on both AC and DC. Right, so what is the drawback of DC shunt motor? That it will not produce the enough starting and running torque. Why? Due to the more number of fine wires, more number of turns of fine wire. Due to what? Due to the more number of fine wires, there is the inductive effect, right? And due to that inductive effect, there is a high reactance and so high impedance, and that's why there is a low field current and that is much lower than the required to develop the sufficient starting torque. So that drawback is overcome here. Why? Because the field winding and the armature winding both are connected in series, and the field winding is with few turns of thick wire, and that's why the inductive effect in DC series motor is less, and the field current and the flux are almost in phase with each other, right? And that's why the rotor current is the same in both field and rotor, and there is no time lag, means there is no any lagging between the flux produced by the field coils and the current in the rotor conductors. That's why the DC series motor can operate easily on both AC and DC. Now we'll see the performance of the DC series motor when connected to single phase AC supply. It is found, however, that an ordinary DC series motor when connected to single phase AC supply operates but not very satisfactorily. And what are that reasons? That we'll see. The first reason is that the torque developed is not of constant magnitude as in DC series motor, but pulsates between 0 and maximum values each half cycle, because the field and rotor currents, means what? That armature current in DC motor both reverse every half cycle, because we know that in DC supply the direction is one, that is what? It is a unidirectional quantity, right? But in AC it is changing the direction continuously after half cycle. That's why whatever the torque developed when DC series motor is connected to AC supply is not of constant magnitude, but it is having some pulsations from 0 and maximum values after each half cycle, right? Why? Because the field and the rotor currents both reverses every half cycle. So this is the one reason. Then second, the alternating field flux would induce eddy currents in the solid parts of the field structure, such as the yoke and cores, causing excessive heating and lowering of the efficiency. Then third reason is, so as shown in the figure, that is from the figure, an ordinary series motor, it is clear that there is no inductive coupling between the field and armature windings, means what? Between the stator and rotor winding, as they are placed in space quadrature, right? So here armature is what? It is the rotor winding and field is the stator winding, right? So from the figure, the armature indicates rotor winding and field winding indicates the stator winding. So here from this diagram, so it indicates the schematic of an ordinary series motor, and it is clear that there is no inductive coupling between the field and armature, means between the stator and rotor, as they are placed in space quadrature, means they are 90 degree in 90 degrees from each other. So as a consequence, both the windings act as open circuited primaries. That are acts as open circuited primaries of the transformers, and therefore each winding has large reactance. And this results in small current and abnormal voltage drop, and that's why reduces the output and power factor to such low values as to make the motor impractical. Got this? So due to the space, that is what as they are placed in space quadrature, that's why small current and abnormal voltage drop occurs, and that reduces the output and power factor to such a value that makes the motor impractical. Now the fourth reason is when a series motor operates on DC supply, it develops rotational EMF in conductors. It develops rotational EMF in conductors placed along the brush or Q axis due to the armature reaction flux. So the self-induced EMF, often called the reluctance voltage, and is developed in these conductors due to the reversal of the current in them on crossing the brush. So in case of AC operation, in addition to rotational EMF and reluctance voltage, transformer EMF is also developed, which will be maximum for conductors, that is for conductors A and B, that is indicated in figure on brushes, right? So that's conductors lying midway between the pole centers, because the armature coil with the greatest EMF is the one whose magnetic axis is parallel to the main field, and consequently at the commutator the voltages developed by transformer action are greatest between segments just where the brushes are situated at the so-called neutral points. So the result would be destructive sparking if measures were not taken to limit the current passing between segments short-circuited by the brushes. So these are the reasons when an ordinary DC series motor connected to single-phase DC supply will not operate satisfactorily. Right? So however, of larger voltage drop in the machine due to its high inductance, the speed for AC operation is much less than that for DC operation for a given torque. And that's why the starting torque is also poor due to the low power factor at starting. Hence, some modifications are necessary in a DC series motor, that is to operate satisfactorily on AC. Now we will see why some modifications are necessary in a DC series motor to operate it satisfactorily on AC. So the modifications and improvements in design of AC series motors that need to be done are as follows. So the first one is, in order to reduce the eddy current losses, the whole magnetic circuit is laminated, the field magnet system as well as the armature core. For this reason, salient or projecting pole construction is unusual. The field magnet system is smooth cored like the stator of an induction motor. Slots are cut axially into the inner face of the stator to accommodate the main, compensating and commutating windings. Second modification that need to be done in design of AC series motor is, in order to reduce the reactance of the series field, AC series motors are built with a few turns as possible. Fewer field turns per pole means lower flux per pole, which improves the commutation by reducing the transformer EMF in the commutation coils. Third one is, reduction in number of turns on the field winding would also reduce the flux for a given current and would tend to increase the speed and reduce the torque available for a given current. Hence, to develop the required load torque, the number of armature conductors would have to be increased proportionately. Fourth one is, the increase in armature conductors causes increase in the inductive reactance of the armature, and thus there is no reduction in the net reactance of the machine. So in order to overcome this difficulty, the machine is provided with a compensating winding which neutralizes the armature MMF. Next one is to obtain sufficient flux with fewer ampere turns per pole, the reluctance of the magnetic circuit must be reduced to minimum, and this is accomplished or achieved by operating the ion at low flux density and therefore at high permeability and by using a very short air gap, and because of the small number of field ampere turns and very low flux density, a short pole is required. Next one is the operating voltage is kept low in order to reduce the inductance, and that's why high voltage motor with proportionately low current would require a large number of turns to produce the given flux. The last one is interpoles are provided in AC series motors to eliminate the armature resistance leads, and these armature resistance leads occupy valuable space and lower the rating of the motor by their heating. So in brief, we will see these modifications and improvements that need to be incorporated in design of AC series motors. So first one is the whole magnetic circuit need to be laminated. Second one is AC series motors need to be built with few turns. Third one is more number of armature conductors are required to develop the required load torque. Fourth one is to neutralize the effect of armature MMF with increase in armature conductors. A compensating winding need to be provided with the machine. Right? Then the next one is a shorter pole is required. Why? Because of the small number of field ampere turns and very low flux density. Then next one is the operating voltage is kept low in order to reduce the inductance. And the last one is the interpoles are provided in AC series motor. Why? Because of the resistance leads, the rating of the motor lowers due to the heating. That's why the interpoles are necessary to be provided in AC series motor. So these are the some modifications and improvements that need to be incorporated in design of AC series motor. Now we'll see the commutation. In single phase AC series motors, as already explained, two EMFs, that was two EMFs, rotational or speed EMF and transformer EMF are induced in the armature conductors. So whatever the brush position may be, there is always an EMF induced in the short-circuited element of the armature winding. Hence, when the brushes are in normal position, that is perpendicular to the main field flux, right, as shown in the figure, transformer induced EMF is in the short-circuited element, and when the brushes are along field axis, dynamically induced EMF is induced in it. Hence, motor gives more sparking when an ordinary DC motor. Hence, motor gives more sparking than an ordinary DC series motor. Excessive sparking and poor power factor are prevented by providing compensating winding, which carries the armature current and neutralizes the armature MMF. Right, so as shown in figure, the field flux is produced along the axis CD. Right, so there is main field winding and below that there is the CD. So the field flux is produced along the axis CD and armature flux is produced along the axis AB. Right, so there is the AB, brush positions are there, right, and that is what armature flux is produced along the axis AB, and that's why the compensating winding must produce a flux along AB and in a direction opposite to that of the armature flux at every instant. Right, so the compensating winding is placed in the stator slots and its axis is kept at 90 electrical degree to the main field flux. So it may be connected in series with both the armature and series field as shown in figure. So the number of turns per pole in the compensating winding is so chosen that the MMF produced by it is equal and opposite to that of the armature. So in this case, the compensating winding carries current equal to that flowing in the armature but in the opposite direction due to conductive effect. So it is known as conductively compensated series motor. Now we'll see the combination of main field and the compensating field. So for that, see the first figure here with the armature and field winding and with the AC supply. So here it is possible to combine the main field and the compensating field by employing a single distributed winding which produces its flux in the direction of the resultant flux of the main field, and compensating windings, right, as shown in figure. And another method is to short circuit the compensating winding as shown in this figure with the short circuited compensating winding, main field winding and AC supply, right, and the armature with the brushes. So this is the another method, and in which the compensating winding is short circuited so that it behaves like the short circuited secondary of a transformer, of which the primary is the armature winding, and that's why in this case the compensating winding is excited inductively. So the motor with short circuited compensating winding is known as inductively compensated series motor. The current in the compensating winding will be almost directly proportional to the current and practically 180-degree out of phase with it. Therefore, the action of the compensating winding will be almost identical with that of a conductively compensating winding. The resistance and inductive reactance characteristics of the armature circuit of the inductively compensated motor will be increased over their values for the armature by a certain amount through the coupling of the compensating winding to the armature in accordance with the transformer action, and that's why the total resistance and reactance characteristics of the inductive or inductively compensated motor are practically the same as those for an equivalent conductively compensated motor. So that's why in real the performance characteristics are practically identical for the two types of series motors, right? So the performance characteristics for these two types of uh, AC series motor is same. Hence here the unit 6 is completed, and we understood in this unit of special purpose machines different special purpose and fractional kilowatt machines, and now we are able to describe or explain the construction, working, characteristics and applications of synchronous induction motor, induction generator, permanent magnet synchronous motor, linear induction motor, then single phase synchronous motors, that are reluctance motor and hysteresis motor and AC series motors. We are also able to differentiate the AC series motor and DC series motor, then to compare the linear induction motor and three-phase induction motor according to their construction, right? And also we can answer to any type of questions related to this machine. So thank you.